All right, benzyne, section 16.7. 16.7 in our textbook introduces us to the concept of the benzyne mechanism. What does that mean, benzyne? Well, what does "ine" mean to you? It's a triple bond, right? Triple bonds have sp hybridization. They have linear geometries. Benz. We're in this chapter on the chemistry of benzene. So this part tells us benzene, of course. So if we put these together, what we're going to see here is the way scientists decided that we have a very strained species called benzyne. This is a fleeting intermediate in chemical reactions, but it is our best mechanistic hypothesis as to how we explain the chemistry that we observe. Now, I should point out to you at this stage, mechanisms are hypotheses. They're theories. They start out as hypotheses. They become theories for which all of the available data support the conclusion of that particular hypothesis, and so we call them our theory. Of course, mechanisms in chemistry, like most theories in science, cannot be unequivocally proven. We can disprove other things by an experiment that will not fit with the data of our hypothesis, of our theory, the benzyne intermediate. But so far nobody has come up with something better or an experiment to disprove it. This is a critical thing for you to understand about science. So, how is it that benzyne happens? Well, in the last section I told you that we needed a strong electron withdrawing group to do a substitution reaction on a chlorobenzene to produce an alcohol, the phenol. Okay? But it turns out if we treat this with sodium hydroxide in high temperatures, like 340 degrees Celsius, and the number reported in your textbook, 170 atmospheres of pressure, then we can actually affect this change. That is the substitution of chlorine for hydroxide. Okay? And so this is the benzyne reaction, and it's based off this benzyne mechanism. So one of the first things that people did was to begin to experiment with this and do physical organic experiments. I think the example is a bromine. So with bromine, they went to the trouble of synthesizing a benzene that had a label at this carbon. Guess which label? C13, because we can see it easily in the NMR spectrum. They treated this then with a good nucleophile, which is also a strong base, potassium amide. This, of course, was done in ammonia as the solvent. And when they did that, they found that this C13 label had scrambled. There were two products. The product where the nitrogen was now bound at the same carbon that the bromine had been bound, but there was another product. And what I'm going to do here is I'm going to keep the label in the same position, so the carbon is still there, but the amino group was at the position ortho to that label. So how could this occur? This obviously cannot occur by the addition-elimination mechanism that we just saw in section 16.6 for nucleophilic aromatic substitution. Okay? Remember there, the benzene was an electrophile. The hydroxyl nucleophile attacked the carbon containing the leaving group, and then it left. So that meant that if we'd done a labeling experiment there, we would find that we only had substitution at the labeled carbon. Someone has done all these experiments, by the way, somewhere buried in the old physical organic literature. Now, this particular experiment, how do we understand this? Well, the mechanism that people have come up with for this reaction is an elimination addition mechanism. Now, the order there is important. Remember, nucleophilic aromatic substitution, the last reaction was addition first and then elimination. So, what happens here? Let's take a look. Our species, get some ink back. We're going to perform an elimination reaction. So we need that hydrogen next to this system. This then will react with our base. Oh, let me back up. This should be a bromine. So we have our substrate here. It's important that we recognize those ortho hydrogens, because to perform an elimination reaction, we need that hydrogen there to be eliminated. So our strong base here reacts as a base. So how does it act as a base? This produces benzyne plus ammonia. Now, if we had our label here, there's where our label would be. Now, this benzyne intermediate is symmetrical except for that C13 label. Okay? And here's one of the key facts that I have left you in the dark about till now. These were present in a 50-50 ratio. Okay? And again, this benzyne intermediate explains this, because now we can have another amide attack, and it can attack either end. We'll call that one A, or this one B. Okay? If it attacks at A, we would get the labeled product at the carbon with the nitrogen. There's our label, path A. If it follows path B, our label will be there, and the NH2 group is here. Okay? And then these just pick up a proton. This is a very strong base. This is a phenyl-anion. And so they will, from ammonia, pick up that proton, and that gives us product. PDT is my standard abbreviation for product, just PDT, so we can get there. So this puts the label in the ortho position down this pathway. This pathway puts the label in the ipso carbon. So you push the arrows and finish this and draw these products to make sure that you understand how the benzyne mechanism works.